All right, thanks very much for showing up. Don't forget you can rate all the talks using our specially customized app. You will have received a QR code in your emails with your invites. If you haven't got them, you can always scan the QR at the reception desk and rate the talk the way you want it, and you want to give all those talks 5 stars, obviously. Like this one, prepared by our next keynote speaker, Herb Sutter. Now, Herb is an author, consultant, speaker, designer, and co-designer of various ISO C++ features and chair of the ISO C++ committee. He's also a programming language nerd whose focus is on enabling our program code to be both clean and fast. Clean and fast? You must be a magician as well, Herb. No? As you know, we always like to collect fun facts about our speakers, and to do this, we asked Herb about his favorite Star Trek movie, and he immediately said, Galaxy Quest. Just to explain to those who have no idea what I'm talking about, Galaxy Quest is a parody of Star Trek. Anyway, peering forward, C++'s next decade. Let's have a big hand for Herb Sutter.
Thank you all for coming. May I just learn a little bit about you just for a moment? So I'm going to ask 3 questions, and if you could cheer to let me know your answers if it applies to you, all right? So Bjarne just showed us that he's been working on C++ since 1979. By my calculations, that makes C++ 45 years old. Think of your age. How many of you are 45 years old or younger? Can I hear you? All right. You know what's next? How many of you are over 45 years old? Okay, fewer, we're gray, but we're feisty. And how many of you kind of like C++? Well, good. Then you probably won't be bored for the next 45 minutes because Bjarne has talked a lot about where C++ has come from and where it's currently in progress of going. And I'm going to take a bit of a risk by going forward to the next decade, because I think what we have learned about C++'s trajectory this year is informing us very well for what to expect in the next decade. The usual disclaimer applies. Prediction is very difficult, especially about the future. Yogi Berra. But let's take a look at what is coming, what is in progress, and what it will mean for our next decade. I'm going to talk about reflection, and I'm going to talk about safety as the 2 main topics, but then talk just a little bit about how that helps with simplicity as well. And there's an intersection between those 2. Reflection and safety may seem like unrelated topics, but they are related in timing because they're both starting to land significantly, it looks like, fingers crossed, in C++26. They are related technically, which is probably not obvious, in that both are about greatly reduced undefined behavior, and both of them will simplify what we do. So let's see first, what about reflection? What is it, and why is it going to be so impactful for us in C++? The short definition of reflection is that it lets the program see itself. And generation is to let the program generate more of itself. So usually I'll say reflection is a shorthand for both reflection and generation, because I think generation is part and parcel of it. But I'll often mention both just to emphasize it's not just about reading, it's about also generating more source code. So when we think about generative C++ styles, that's going to be something that we have very little of today. mostly in forms of very obscure patterns, common but obscure, like CRTP. And if you know what that means, you know way too much C++. But we're going to really increase the support that we have for doing this. And because all of this is done at compile time and the program is reading and writing itself, of course, that's very meta. That's what meta means. And so we call this meta programming. But I want to make one big distinction, because if you are familiar with reflection in other languages, this has an important difference. So in Java reflection is important. If you make a virtual call using reflection versus doing it directly, it will be 3 to 5 times slower, because it's runtime reflection in Java. And it's still super powerful. It's still very popular, enables many styles. But this is C++. That's not how we roll. In C++, we are looking at reflection that is purely at compile time. Now, that does not mean that you can't compute something at compile time and then store it in a data structure to use at runtime. You can save the data and use it later. But unless you do that, you pay 0 runtime overhead for using reflection. This is not something that's new. As Bjarne just mentioned in the previous talk, this is part of a 30-plus year arc toward more and more compile time programming in C++. And as we're looking at bringing this into the standard, the very first proposal that aims, if fingers crossed, if it succeeds, if in the next 2 meetings we can do it by June of next year, to put reflection, the first parts of reflection, into the standard. That's proposal P2996. We like to talk about P numbers because that's what we do. So you'll hear that number a lot from standards committee members, but that's the first main proposal to add the first step of reflection. So into hopefully C++26. Hopefully that will succeed, but that's not the end. So if you look at that and you say, oh, but there's not really generation yet, that's okay, because there are already other proposals to introspect more kinds of things, to actually then cross that dotted line into actually generating code. There are prototypes of many of these available, and I'm going to show a little bit of code, but these are stepwise. Not all of them will be in the first release, but we're going to be building these out, hopefully starting with C++26. Now, here's one of many examples. I actually chose a short and simple example from 2996 so that we can absorb it in real time on a slide. But if you're interested, and I suspect many of you are, please go to that paper and you will just search for WG21 P2996. You will find it. It has many examples, many of them intriguing, including a more advanced example of what I'm about to show you. So thank you, Matush, for this example. Here, what we have is a program that is a very simple command line argument parser. And the idea is that I have this struct, my options, and this is going to define what are the command line options that I want in my program. I have a string file name as one option, and it will default to input.txt if you don't write one, if you don't write it yourself. An integer count that defaults to 1. And then in my main line, I'm going to call this parse options function and pass it the type myOpts as a description of what I want my command line parameters to be. Make sense? Now, so far, this may look like normal C++ as we have been using it for years, but there's already something a bit different in how this works, because after I call parse options, it's going to return me an instance of my opts that has opts.file filled in with a file name, opts.count filled in with an integer count. One's a string, one's an integer. And if you're reading this code and you're starting to think, oh, but I can see how most of that works, but wait, how do I at runtime match a runtime string on the command line that matches this compile time name of the data member? Then you're asking the right question. So here is a look into the implementation, and I'm highlighting just a few key parts to pay attention to. Again, at first, this looks like a normal piece of code. Template, type name, opts, and then there's our parse options function, and it's going to take a runtime span of string views. These are the command line arguments, whatever it is the user wrote on the command line. But notice in this case, the first thing I do is I have this new thing called template for. The syntax might be tweaked, but right now in the prototype where this works on godbolt.org, on Compiler Explorer, this works as template for. And notice that I am iterating over the non-static data members of, and then there's this funny new thing that we just decided a couple of days ago, this is what the syntax is going to be, is this double hat. It is some people are trying to get it to be called the unibrow operator, which is saying, you see this type, you passed me a type. Templates have been doing this for years. Here's the new thing. I am going to reflect on that type, and I'm going to look at the structure of the type. And this is something new. This is something we could not do before. And I'm actually going to have a compile time range for loop over the data members of that type. And I'm just going to go and see, and I'm going to call ranges find if. This is normal C++ code. And I'm going to see if one of the variable names in the type, which is compile time, matches the runtime string the user wrote on the command line. And if it does, I'm going to go, so the type itself is a function input. The structure of the type is a function input in a new way that we haven't had before. I'm going to use this expansion statement, reflect, and use these meta functions, and then I can do error checking, and then finally notice there's this funny thing called a splice operator. What this is saying is, all right, I figured out the command line, the member of the struct that I'm trying to match. That's the command line, switch that the user specified. Take that name, which I just matched the user writing at runtime, stick it in at compile time to the program, because I matched it so I know it's the right one, and try to take whatever the user wrote as a string value for that command line option, and stream it using the normal I/O streams into opts.thatName, into that member of the option struct. Now, what this will do, it will do a type-safe conversion, which will also fail if the input is not of that type. Like, let's say that it's an integer, it's supposed to be an integer parameter, but you gave it something that's not, the user wrote something that's not an integer. This is type-safe. We will catch that. And then we can give a nice error message that if you gave the wrong type, we can say so. So here's an example, just a screenshot from this working on Compiler Explorer today, where if the user wrote --count42 and --file name Scott Meyer's Effective Modern C++ PDF, because of course everybody should be reading that book, then we can see that opt.file has been given the string value, Scott Meyer's EMCPP PDF. Ops.count has been given the integer value, 42, which has been converted from a string to an integer at runtime, but we've been matching the struct members to specify the command line options at compile time. And it's type correct, because if you try to say, oh, give me a count of Scott's book, well, what does that mean? That's not an integer. Count must get an integer. I don't know, you mean the page count, the word count? No. You need to specify an integer, and you can say, sorry, count is not a valid int, because this is all type safe. So to find out more, there are a couple of current implementations that are tracking this. One is based on EDG by David van der Voorde, and one is Clang-based by Dan Katz of Bloomberg. And there are other related efforts, including my CPP front compiler, but those first two ones are implementations of the actual proposals currently being progressed in the Standards Committee. So you can find them both on Godbolt. So now let's switch gears and talk about that second topic, about safety. This too is part of what's going to dominate C++'s next decade, because just as we've just talked about reflection and how it enables a whole new method of programming, and where we're going to be delivering parts of it, hopefully starting in C++26 and then over the coming years, it's also going to take us a decade to learn how to use it, to learn what's possible. So I expect to see a spurt of growth of experimentation and learning, and really pushing new boundaries in doing things that were impossible or impractical before in C++. And it's going to take us a decade to absorb this, and it's going to be fun to learn how to take good advantage of this new power that we've never had before. But putting safety first in C++ is also kind of a new thing, because we've always taken the view that, well, safety is something you could always write safe programs in C++. But you had to really pay attention. And can we do something to still stay C++? So we're not turning ourselves into some other language, to stay true to our values and ideals and talk about backward compatibility, but still do something substantial about safety. Well, I wrote an essay about this earlier this year. The link is at the bottom. And the actual problem that I argue we should be looking at in the near term is, first of all, parity, not perfection. And what I mean by that, parity means being the same. So there is no perfectly safe, perfectly type and memory safe commercial programming language. There is not one. Now, there are ones that are much safer by default than C++, and we call them memory safe languages because they are substantially safer. And the ways to go wrong, there are fewer ways to go wrong. For example, in Java and C#, in purely safe code, I'm not talking about using unsafe escape hatches, just in safe code, you still can use an uninitialized variable. For example, by doing a virtual call in a constructor, because in Java and C#, virtual calls are deep. Therefore, if you call a virtual function in a constructor, it will dispatch to the derived type whose members have not been constructed yet. And this isn't something where we say, oh, look, they're unsafe too. No, that's not the point. They're definitely safer, a lot safer, and there are fewer ways to go wrong. But they're also not perfect too, and that's okay. They teach their programmers, don't do that. Be aware of that edge case. So it's okay for us not to be perfect either, but we want to get to the same level of safety. That is something we want to do, and where we have to do real work to get it. And there are 4 specific areas that we need to do. This is not excluding other areas. Concurrency safety and other things are important too, but the first 4 main important ones are type safety, bound safety, initialization safety, and lifetime safety. Initialization is part of type safety, but I'm going to split it out especially. But when you look at bounds and lifetime, sometimes you'll hear terms like spatial safety and temporal safety. They mean roughly the same thing here. So why am I saying those are the 4 important ones to look at first? Again, not excluding concurrency safety, but we're interested in that too. But why is that something that we can look at longer term? Because these 4 have 2 important properties. These 4 are year after year after year the 4 biggest causes of memory safety vulnerabilities in the field for security issues, for security incidents. They're what attackers are exploiting. Second, these are the 4 that every single memory-safe programming language does better than C and C++. By definition, if we had parity, roughly the same error count, that it's roughly as difficult to write bugs by accident in these 4 areas as other programming languages, we wouldn't be having a conversation about moving to other languages, because we'd be the same. Now, again, concurrency safety is also interesting, for example. We should be looking for that too after these, because of the commercial languages, the memory-safe languages. Only Rust currently tries to give concurrency safety guarantees, which is great, but it means you can be a memory-safe language today without that. So we all should be trying to raise the bar and achieving those things too. Safety, good, but here's what our focus ought to be. And so we've been making great progress in that. We've already, in the C++20 standard, for example, standardized span of T so that we can actually say use that instead of pointer arithmetic because the span knows its bounds. We have started removing safety-related undefined behavior. I'll have a bit more to say about that. And we're working on static safety profiles with mostly static and also dynamic checking where necessary, where we're taking some well-known rules already and moving them to compile time so they run on the developer's machine before check-in. That's important. And of course, there's other work going on, such as -F hardened, and implementations are giving you more security guarantees as well. But it's really important that we're not talking about changing C++ into something else. It is true that we have some pretty sharp knives. Do you feel like you have some pretty sharp knives when you're writing C++ code? Do you have like nicks on your fingers sometimes, some Band-Aids? Yeah, it's a tense chuckle because we've all been there, right? But we need the sharp knives. If you're going to have a Michelin chef, you can't have a Michelin chef who needs to do all sorts of things and then take their sharp knives away and say, sorry, we should only give you safety scissors. Well, they can't do their jobs. C++ programmers can't do their jobs without the sharp knives. And besides which, if anybody came up with a proposal that would try to take your sharp knives away, out of my cold dead fingers, right? Nobody is going to take a sharp knife away from a C++ programmer. The problem, though, is it's too easy to use a sharp knife when you didn't mean to in C++. And to me, that is like having a kitchen that is full of knives that are just lying around on the floor and on the counters, so you have to watch very carefully where you step. And it's like writing code where you wrote something unsafe by accident. You didn't mean to, you were trying to be diligent, but it just compiles and silently runs and doesn't do what you expect and you may not notice. And that's way too easy to do in C++. So today, that's kind of like we say, well, watch out. C++ is performance and control by default. That's where we came from. Safety is always available. So when people say, I can write safe code in C++, that is both true and beside the point. Because it is absolutely true, but it's just very much harder than in other languages. So I propose that what we ought to be doing is staying in the same kitchen with the same knives. We love our C++ kitchen, we love our sharp knives, but just flip that to safety by default and performance and control always available. Just put the knives in a drawer. That's all. That's what safety profiles are for. So that's the whole idea of them, is just take the knives, just put them in a drawer. The drawer is not locked. You can open it anytime you want and take out any knife you want. But now you can walk around on the floor without cutting your toes by accident, nearly as much. Here is something we've already done earlier this year, and this is, between this and reflection, I actually view 2024 as a pivotal year where we have started to make major changes for the first time that affect users broadly. For I think the first time since C++11 to that level of magnitude in terms of the impact it's going to have on the way we write code that starts another cycle, another generation of C++. Now, we all know about undefined behavior. How many of you are super familiar with undefined behavior? Yes, right? How many of you would like to be less familiar with it? Right, so the problem with undefined behavior is anything could happen. And we say, oh, you know, demons could fly out your nose, it could format your hard drive, which is a slight exaggeration because what actually happens is merely time travel and leaking secrets and creating security vulnerabilities, and that is plenty bad enough. So in March of this year, the C++ Standards Committee adopted what may seem like a very small thing, a new kind of behavior. Now, we've always had well-defined behavior. The standard says exactly what this code does, and a compiler has to make it do that. We've had implementation-defined behavior. That is, the standard doesn't say what will happen if you write this code, but your compiler manual must tell you exactly what happens. It must be deterministic. And of course, undefined behavior. Well, we've now got another one of those called erroneous behavior. This may seem small, but I'm going to explain why I think it's really powerful. It is well defined as being just wrong. And let me just walk through that. This means it is something that is legal C++ code, but we say, yeah, even though we let you write that in the standard, it is wrong for you to write that, and we are going to officially take note that that is wrong. And we're going to say it must have a well-defined result that depends on your compiler, but it can't be undefined behavior. Now, to give you an example of why this is so important, this means we can take things now that were undefined behavior and make them erroneous behavior, and just by doing that right away, there's no time travel, there's no leaking secrets for that. And the first place that we adopted it, this general tool, was as of C++26, reading uninitialized local variables is no longer undefined behavior. If you just take your existing source code and recompile it with a soon-to-come C++ compiler, C++26 compiler, it will be safer. I'm going to come back to that because that's a super important adoption story. So what does a C++26 compiler do instead? Well, if you write an uninitialized local variable, it is now required to write something. You can't rely on what it's going to be, but it's not going to be undefined behavior. It's not going to be whatever bits were there before. It's not going to be time travel. It's not going to be an exploitable security vulnerability. And you get that just by taking all your million lines of code and just recompiling in C++26 mode, and you get less undefined behavior and more safety just by recompiling. That is a super powerful story. So here's an example from the screenshot from Godbolt. I've got two functions, and I call F1 and then I call F2. F1, among other things, puts a character array on the stack, which, it happens to say secret. Maybe I don't want other people to know what that secret is. So then I just return from F1. Okay, what does that do? It pops the stack. So now the stack space is not used. But what's in that memory? It's not been overwritten, right? So it's still sitting there. It's now in deallocated memory, deallocated stack memory, but that still contains the secret. And then I call this other unrelated function that just happens to be called next in this particular call site, and it has, look, an uninitialized local variable, just happens to be the right size, but it could be a bunch of ints or something else, and it will see by default the bits that were already there because you didn't initialize it with anything. If you print this local variable, which has nothing to do with this one, today the comment says this likely prints secret. It prints secret on GCC. It prints secret on Clang. It prints secret on MSVC. That is not good in a world where software security and software safety are important, because this is a form of memory unsafety. Take that same code, just recompile it with a C++26 compiler, and today, even before C++26, on the right-hand side of the screen, you can see the switches you can use on GCC, Clang, and MSVC today to get the same effect. And that just goes away. I have not changed the source code. All I did was recompile it with, today, these non-standard switches on the right, and in the future, with no special switches at all, just by recompiling it in C++26. Now, I want you to think about what this means. Quantitatively and qualitatively. Quantitatively, this automatically eliminates some fraction. It's not a majority, but is it like 5%? I don't know. That's still a large number of security vulnerabilities and other bugs. Just automatically eliminates them. That's a major step forward. But qualitatively, how do I deliver it? Like, if any of you ship a product, how many of you have ever in your careers shipped a product and been sad when customers didn't adopt it as fast as you would expected that they would? I see a few hands. Like, that's happened to all of us, right? When we design a new product, even if it's the next version of an existing product, we have to pay attention to adoptability. How easy is it for customers to use our new product, to use our new feature? This one is delivered in a way where all I do is take my existing code and recompile it, and it just gets safer. That is the holy grail adoption story. Zero manual code changes. I just take my existing code, compile it in C++26 mode, and it has less undefined behavior. It is safer. And this is just the first step, and we're going to be doing more of these things. But I love to see how the committee has shown it is serious, not just about improving safety, but doing it in an adoptable way. That's not some ivory tower, make all these changes to your source code and then it'll work. Like, sometimes that's necessary. I don't mean to disparage that as always being ivory tower. Sometimes that's necessary. But when we can do better, everybody is so much better off. We get our features adopted more, users benefit more, and we improve the world's C++ code and make it safer. So one of the major efforts happening that you'll see entire other talks about is the safety profiles framework. We had the first set of safety profiles that came into the main evolution working group just a few days ago last week. And so if Bjarne and I can do, and helpers can do a whole lot of work over the winter and sacrifice our winter break, maybe we can start getting some of that even into C++26, because we believe it's an urgent thing to start getting type and memory safety profiles. I think of them as warning families, as a set of rules enforced at compile time. They guarantee that certain kinds of defects just can't happen if your code compiles successfully, and to make it easy to opt in and opt out, and to be selective and incremental about that. Many of these rules are rules we already know, but we want to shift left. That is, we want to take them from maybe some post-build static analyzer and run them at compile time, typically in the compiler, like a warning family, but also with a view to adoptability. To the extent possible, I'm proposing that we get some of the benefits of profiles, at least, just by recompiling our code. So much more detail on that is to come. And finally, let me just give one example, because there isn't time to go into I have quite a few examples of how both reflection and safety will help with simplicity. But as we're already talking about safety, let me give just one example. And again, I want to draw a line here between what the Standards Committee has approved and what I personally am proposing. However, what comes next is something that I am personally proposing that just a few days ago, for the first time, the Standards Committee seems to like. So it still needs to be approved, but it's already partway through approval, and I think it's something that will help us. So let's start with reflection. So we're going to talk about safety and simplicity, reflection, and then safety. One of the things I'm proposing is a small but important syntactic sugar, so that if we write this code, which we can already write in the P2996 prototypes, that it will let us declare classes. So we write classes to say, hey, I'm not just writing any class, I'm writing an interface, I'm writing a value type, I'm writing a container, I'm writing a proxy, those kinds of things. And to have a syntactic sugar so that the code on the bottom is merely sugar, but important sugar for the code on the top. So the idea is today we can write an interface in C++, an abstract brace class like this, but we have to remember most of those lines. And it would be nice if we could just say, hey, here is a meta function which uses reflection and generation to say, take the ifoo that I wrote on the right-hand side, just take that source code and generate all these defaults, generated functions, and checked constraints. Make my functions virtual and pure virtual by default. Declare my pure virtual, declare my virtual destructor if I didn't already. Make sure I'm not copyable, and force a rule like that I don't have data members, because an interface shouldn't have data members. This makes programmers' lives simpler. It also makes tools simpler. So if you just look at, say, Qt. Qt is one example of a system where we have to have extra annotations outside the source code today that we could get rid of in the future using reflection and generation. The details are in my paper P707. But if we could write the code on the right-hand side, which I showed first on stage at CPPCon 2017, 7 years ago, and is now getting real, not only does that mean our code is simpler, not only does it mean our code is more robust because we have fewer ways to go wrong because the boilerplate is being generated for us, but also our our build tool chains can get simpler. Ideally, we could get rid of side compilers that parse and process the extra annotations and put it all inside the single C++ compiler using reflection and generation. So not only is our source code simpler, but our build systems could be simpler. Now, this isn't going to happen in year one, but this is an evolution that I can see happening over the next decade, and I know that vendors who have these build systems are just waiting for this. Similarly, in COM at Microsoft, you have these extra IDLE style extensions. It would be nice to be able to avoid all that boilerplate in the side IDLE language by just declaring our intent and doing the equivalent using reflection and generation. And that gives us a much simpler build model than either C++CX or C++WinRT. And people are doing this themselves. Here's an example from Benedikt Hegner and Axel Naumann from CERN, where they have a YAML script that generates 5 related C++ classes from every class defined in the YAML. And they could simplify their tool chain as well. When I showed those examples 2 months ago at CPPCon, I gave that talk. It was over. Finally, I could relax a bit. I could stop worrying about my slides. The next time, so I went to my room and relaxed. The next time I left my room, next morning, I thought, okay, I'm going to go down and get coffee. All right. So I walk out of my hotel room, start walking down the hallway. Between my hotel room and the elevator, I met a conference attendee who said, hey, great talk. I can't wait for reflection. You know, we have one of those code generators, those side code generators in our team that we use to generate C++ source code. This, what you described, would let us get rid of that. We would love that so we wouldn't have to maintain that thing anymore, and we'd have a simpler build model for our project. Oh, hey, that's great. So he joined me. Elevator doors open, we get in, doors close, we go down partway. The elevator doors open, another person comes on, neither of us knows, says, oh, hey, I liked your talk yesterday. Do you know that we have at our shop a custom code generator that could... And in Berlin a week ago, I asked for a show of hands, how many people have that at their shop? And something like two-thirds of the people raised their hand. How many of you in your current shop have something like a code generator that is generating C++ code for your project? Yeah. Don't tell me that people aren't aching for reflection and generation. Do not expect people to take 10 years to adopt this feature. This will be adopted like hotcakes. And this is C++'s next decade. It is going to dominate, I think, our next 10 years of C++ by making things easy that are hard today, but more importantly, by making things possible that are impossible today. You know, I gave the example there of example of C++CX. I was the lead designer of C++CX, which was a set of non-standard extensions to C++ in the Microsoft compiler. I was also the designer of C++ CLI. I led the design team for that, non-standard extensions to C++. I've been saying since that 2017 talk that part of my motivation for pushing for reflection and generation in the language and meta-class functions is because I don't want to ever have to design C++ CLI or C++ CX again. I know what it takes to do it. The reason we did it was because we couldn't express all that information in the C++ source code. I want to be able to write it all in C++, and I couldn't 15 years ago. But soon we will be, 20 years ago for C++ CLI, but soon we will be able to do that. And finally, one note about how safety can simplify our code. And this is the adoption story I was talking about. So this is the feature I'm proposing, but that just a few days ago, the Standards Committee started showing some interest in, so I am not advertising that this is for sure in C++26, but fingers crossed, there's a chance it might be. And I've implemented this in my CPP front compiler as a proof of concept. Now imagine in your source code, every time you have a subscript expression of the form A subscript B, right? If A is a container that supports std size, and if B is an integer, at the call site, right there in that subscript expression, the compiler can, and CPP front does by default, generate a bounds check. And I happen to also have implemented a version of the C++ draft proposal for contracts, and a violation is reported through violation handling. We can do that other ways, but that's what I happen to have implemented. But what's the benefit? Because often when we think of bounds checking, like a bounds checked span, I want a bounds checked vector. But if you do it that way, if you do it intrusively, where every container and every type has to implement bounds checking separately, I got to wait for my library vendor to do it and to ship me a new one, a new library. It probably won't have an ABI issue, but it may have maybe skating on that ODR line, like having an assert in the body, where yeah, the two functions, safe and unsafe, if they're built with and without checking, aren't the same, but close enough comdat folding, it can make a squint and make it okay, so it's not a violation. I don't have to worry about any of that stuff. Furthermore, because this bounds checking is done at the call site, as soon as I implemented that, ever since I've implemented that, I've been using the GCC standard library, the Clang standard library, the Microsoft standard library with full bounds checking for everything for 2 years now, and it's great. I have bounds checked span. I've been using it for 2 years. It's great. Bounds checked vector, bounds checked ranges, bounds checked views, and you know what else? Bounds checked Qt non-standard Qt containers that support std size, because that is a well-known idiom that many third-party container libraries also support. And it just works. I just compile the code, and I didn't have to get a new library. I didn't have to wait to update the standard. And so my proposal, which I hope succeeds, and we're going to work over the winter on the initial set of profiles, and this is one detail that's in that paper, I hope that maybe for C++26, like holding my breath and crossing my fingers and toes, that you might be able to recompile all your existing code with the bounds safety profile on and get full bounds checking for all your subscripts. Now, it doesn't check your iterators. Iterators are harder, and that can be an ABI break. But all your subscripts, that's already another huge step forward. And it's important because of those four main safeties. Remember, type, bounds, initialization, and lifetime safety. Bounds is the easiest, and it's the most important to make progress on, because in like the top 4 or 5 security common weakness areas that attackers are exploiting, out of bounds read, out of bounds write. They're always in the top 5. They're the worst pain point, so it makes sense to start with that. So here is how I live in CPP2 right now with either of those two definitions of A. Uncomment either line, maybe into the C array or into the std vector. I actually wrote code like this: print A sub 1, print A sub 2, print A sub 3. You see the problem, right? Off by 1 error. I'm not going to ask for a show of hands how many of you have done this, because we all have. And this is what happens today. So this is a screenshot of what happens if I compile this in the CPP front compiler and the Microsoft compiler. I get exactly the source line, if the source location header is available, where the problem is, the function name, bounds safety violation, out of bounds, attempted access at index 3, the actual range is 0, 2, and this is not hardwired to the Microsoft compiler. The same thing happens with GCC 14 and, on Red Hat, on Fedora. And the same thing happens with Clang. This is something that we could, a taste of the kind of thing that we could deliver in the standard to make our code simpler, our tooling simpler, through reflection and safety improvements as what I see are the two big drivers of our next decade of C++. So I'm excited about C++. I really think that this was a turning point year because we've been talking about safety for a decade. The core guidelines are a decade old. We've been talking about reflection for 20 years in the C++ committee. But this is the year that it's starting to get real. This is the year we put erroneous behavior and eliminated uninitialized locals in the standard. This is the year that we design approved reflection for the standard, both for C++26, and hopefully they'll both get in. We are starting to finally see these proposals land, and this is going to create a beautiful new decade, open up a new, fresh era of C++. Bjarne, for C++26, he made the point that, or C++11 rather, when C++11 came out, he said, you know, there's been so many usability improvements here that C++11, even though it's fully compatible with C++98, it feels like a new language. I think we're about to do that again, and to make C++26 feel like a new language. And then just as we built on C++11 and finished it with C++14, 17, 20, the same thing with this generation. That's how I view it. I am very hopeful for a bright future for C++. Our language and our community continues to grow. And it's great to see us addressing the problems we most need to address. So we have an answer for safety. We have an answer for simpler build systems and reducing the number of side languages to make C++ work in practice. And I'm looking forward to the ride for the next decade and more. So thank you for your time. We have time for a couple of questions, and then we're going to go to a break. Shall we take a couple of questions? You can see better than me who's got their hands up.
Feel free to raise your hands and ask questions, but before that, I think this talk and the author and the speaker deserves a nice applause.
Thank you. Thank you. Yes. Yes, sir.
Hi, thank you for your presentation. Is it on? Yeah, there we go. Thanks. I had a question about the advent of erroneous behavior in C++. What will be the runtime cost of losing undefined behavior? And is there a case-by-case basis on which I can re-enable undefined behavior?
Excellent question. So every time that we put something in the standard that could require an overhead, you will always have an opt-out. In this case, if you want to opt out, you can put the uninitialized, no, actually, I keep wanting to call it that, but we renamed it, indeterminate, the indeterminate attribute on that variable, and you'll get your glorious undefined behavior just like you always had it. Oh, great, he's going, yes, fist pump. That shouldn't be your default reaction, but it's okay. We're going to make you type it to get it, right? But you can, remember we said we're not taking any sharp knives away from programmers? You, sir, have your sharp knife,
yeah,
but you just need to write the attribute.
It's a good idea.
So one thing I didn't mention here is one of my papers that got encouraged, and I have a lot of work to do between now and the February meeting, if I want to get some of this in C++26, is I actually proposed that we take a stab at taking all undefined behavior that's safety related, which pretty much is all undefined behavior, and provide a way to turn it off by default. And in case you think, oh my goodness, that's a pipe dream, that's scary, hear me out. A, we already do it in context per code. How many of you were paying attention or already knew when Bjarne said on the slide that context per code has no undefined behavior? Yeah, this is a little known secret. We've been secretly smuggling an entire large amount of code that already in C++ that has no UB. Like literally, there's more and more context per code. It is zero undefined behavior already, okay? But that's at compile time because you basically run an interpreter and interpret everything. What about at runtime? Profiles comes in because profiles give you a way to opt in and out. So here, my proposal is take all of the undefined behavior that we already ban in context per code at compile time. And for each such case, also turn it off by default at runtime in one of two ways. If it's cheap enough, only if it's cheap enough, turn it off by default in the whole language, just like we did with uninitialized locals. And you still have an opt-out if you want it, right? But turn it off by default for everybody. But you're not going to do that for signed overflow, right? Like no, not even C# turns overflow checking on by default. They can't afford it either. So for the things that do require overhead, and that's a poster child, is overflow, disable it by default in a safety profile. If we can do that, then we have the story that you compile all your existing code in a C++ 26 compiler, hopefully 26, or whatever C++ future compiler, with safety profiles enabled, and it has no undefined behavior. Now, it may be slower. You may need to opt out of a bounds check in a loop or whatever, right? But I think this is important because it's pretty cheeky. It's pretty audacious. I don't think anyone expects C++ to put a serious dent in undefined behavior. Never mind actually have a plan to get rid of it. Now, I need to prove this out, but I have a dream. And that dream is that I want to prove out in the next year, not in the next decade, in months, not in years. So, but you'll always have your opt-out, sir. You will always have your sharp knife. You will not lock your drawer. You can always open the drawer.
That sounds very hopeful. Thank you.
Yeah.
Thank you so much. One question over there, please. Not far from the camera.
It's coming from your other side.
Thank you.
Hello. Thank you for the talk. It's working. Thank you for the talk. I really appreciate the effort for simplicity, but I cannot stop feeling that this syntactical legacy seems to still holding you back, or us back. And the introduction of this double hat operator is like really nerdy, and by heart I love it. But on the other hand, I feel like one day we're gonna wake up and think that, oh no, we're writing in Perl. So what's your take on that?
Sure, and I'm going to not throw pearls before, never mind. There's too many Perl jokes. Your code will not be littered with reflection operators. You will be able to write powerful libraries that use reflection, and then you just use the libraries. Like that command line library, the call site saw no reflection at all. It just called a template. It just passed a type. The implementation got to be powerful on steroids like you've never seen before. It's the Arnold Schwarzenegger of implementations, right? The 1970s, 75 Arnold Schwarzenegger, not the 2024 Arnold Schwarzenegger, right? He's pretty good too, more facial hair. But it'll be in libraries. My other answer to that is, can we keep adding to C++ and make it simpler? And the answer is yes, we can, if we're careful to add features that let programmers directly express intent that they couldn't before, so they can now express what they want to do rather than how to do it. And a poster child example for that is the range-based for loop. Every single one of us could write a range for loop by hand. Iterator equals begin, iterator doesn't equal n, plus plus I. You could do it, but it wasn't declarative. The compiler couldn't see or the human reader couldn't see just reading the first line of the loop that it visits every element once. The range for lets you directly express your intent. Yes, it made the language a bit bigger because we added a language feature, but it made C++ source code simpler. It made it faster because now compilers can see that you've expressed your intent, and just looking at the first line can hoist a bounds check out of the loop. That's faster. It doesn't have to analyze the loop to see if you're only incrementing and checking end every time. It doesn't have to work nearly as hard. It's features like that. And of course, we have to be careful not to add features that only do this one little thing and it's complex and doesn't fit with the rest of the language. We definitely have to avoid that. But to the extent that we take things that programmers are already doing, but they're doing it manually, and we let them express what they want to do so they can, that's what metaclasses are all about. So I write less boilerplate and express my intent directly. C++ code can keep getting simpler even as the language does grow. Yeah.
Any more
all right,
questions,
well, thank you
please?
all.
Yes, one over there.
Oh, we're going to take another here. Right on the aisle. That's very convenient.
Yeah, thank you. So one direction is to extend C++ and the features, but another direction is, which you partly follow, is CPP front and other sort of alternative implementations or simplified implementations of C++, like Carbon language from Google. So what is your opinion about that direction?
So in a nutshell, in another talk I've called this if you're going to make like a 10x improvement to an existing thing, I've called it the TypeScript plan and the Dart plan. So both of TypeScript and Dart, the reason I say this is not to be pejorative about because Dart had other issues that were political and stuff, but I just mean technically that both tried to do a major improvement over JavaScript, right? One of them competed with JavaScript, and that gave Dart a lot more flexibility in being able to do things differently, but they didn't coordinate with the ECMAScript committee. They did their own thing, right? Which, that's a valid technical choice. It gave them more design freedom, and they could do things they couldn't do otherwise. TypeScript decided to be cooperative, pure extensions to JavaScript. They work with the ECMAScript committee. I don't know if how many of you know this, but many current ECMAScript features that are standard ECMAScript were TypeScript features. So TypeScript was not just some competing language, it was contributing back regularly to the main language. That's what I call the TypeScript plan. Carbon is great, but I have not seen a single proposal from those people for ISO C++. CPP front is almost nothing but proposals to ISO C++ that I'm proposing for today's C++ syntax. Nearly, like most of my papers in the last decade, even before I announced CPP front and CPP2, came from that work, because I've been doing that work for 9 years now. Having said that, there are a few simplifications that you can only do by actually having a simpler syntax, and so I also have an experimental syntax that's sort of an alternate syntax, but that's still, you write a class, it's still a C++ class. One for one. You write a function, it's still a C++ function. There's zero friction, seamless interop, no thunking, no wrapping, no marshalling, right? It's still C++, but a different skin, like a different syntax. You only need that to get, you know, some simplifications like the simpler grammar and context freedom and order independence. But most things, including the safeties, including about half of the simplicities, including from parameter passing and meta classes, can be applied to today's C++, and that's what I'm trying to do. In fact, I don't know if I'm going to have any time to do work on CPP front for the next 2 months, because the ISO C++ committee just approved so much work for me and Bjarne to do that we've pretty much already promised to cancel our holidays between now and we were not making that up. We actually said that. There's always Christmas 2025. Because the feature freeze deadline for C++ 26 is just a few months away. In June is the feature freeze deadline for C++ 26. If anybody wants to get anything in, they better be working hard this winter to get those specifications ready. And even then, you know, fingers crossed, it depends on if the committee agrees that it's baked enough and so on. But I think the main difference is, are we contributing to improving ISO C++? Or are we doing our own thing? Both are valid answers. You get more freedom if you go do your own thing. But I think it's super important. And why am I spending all this time in ISO C++? Not just because I'm some C++ lover on a fanatical level. You may accuse me of that too. But it's just because I want to have an impact. I'm a user of this world's society and civilization. I use this world's banking system. I rely on this world's hospital system. I rely on this world's power grid. And damn it, I don't want that compromised. I want it to harden it against attack. And if I put all my energy into some new programming language, I will have some impact, but it's going to be much smaller because I can only write so much new code. If I can find a way to just recompile, that's why you keep hearing me say that, to just recompile the billions of lines of C++ code that exist today and make them even 10% safer, and I hope to make them much more than that safer, I will have had an outsized effect on securing our civilization. And I don't mean to speak too grandiosely, but look at all the C++ code that needs fixing. If you can find a way to do that, it will have an outsized impact and benefit to society. And that's why I think it's important, because C++ is important. And not leaving all that code behind and helping that code too, as well as new code, I think is super important. And that's kind of my motivation. Does that make sense? Yeah. I'm sure we need to take a break now. Thank you all for coming and listening to these talks, and you'll enjoy the rest of the day too. There's a whole bunch of great speakers coming.
Herb, thank you so much. Once again, Herb Sutter, everyone.
Thank you.